Hello! Welcome to today's lesson. I'm obviously not here today, so I'm trying to record this at home so that you can listen to it in class and learn about projectile motion. There's one caveat. For a couple of the slides, there are links to little videos, really short videos that I want you to watch. Unfortunately, those don't record well using the Smart Notebook recorder. So when we get to a video, I'm just going to ask you to pause for a second, pause this lesson, open up the video. The links are in the Smart Note, which is posted today as well. Watch the video and then come back to this lesson. Okay, so this is Intro to Projectile Motion. So today what we're going to do is we're going to describe the paths of projectiles when they're given an initial horizontal launch velocity and they're falling due to gravity. We're going to solve some example problems, and then for homework you just got a couple of example problems to try on your own, which are really similar to the ones we're going to do in class. Now, what is projectile motion? Well, in class, the only times we've been throwing things and letting them fall due to gravity were when we threw things straight up into the air and we threw things straight down towards the ground. So we were only dealing in an upward, downward direction, one-dimensional acceleration problems. Today we're moving on and we're going to say, okay, well, what if we launch it? We've got something falling, accelerating due to gravity, but we're also going to give it an initial horizontal velocity. So here's a thought experiment. Let's say you've got two people. One's an astronaut in outer space, not affected by gravity, and one's a basketball player standing on Earth. And they each throw a basketball perpendicular to their chests. What do you think might happen to each of those things? Now, let's just draw it. Here's our basketball player with his basketball. Here's our astronaut in outer space holding the basketball. We know from experience that because the basketball players on Earth, when they release the basketball with some perpendicular to their chest velocity, let's try and get that, there we go, it's going to fall in a nice little parabolic trajectory towards the ground. And that's because it's accelerating downwards due to gravity. That is probably the worst parabola you've ever seen, but let's pretend it's a parabola anyway. But now, here we've got our astronaut in outer space, not affected by any other forces. As soon as the astronaut releases his basketball, the basketball will no longer be experiencing any forces at all. So that the velocity it starts out at will be exactly the same velocity it continues on with pretty much forever until it reaches something else that exerts a force on it. So in this case, the basketball's trajectory is a perfectly straight line with a constant velocity. Our basketball over here, however, has a basketball that eventually falls to the ground and accelerates, but only in the downward direction. So our first definition is for projectile motion. It's the motion of an object when influenced by gravity and no other force. What do we know about gravity so far? Well, based on the lab we did in class not that long ago, we figured out that the acceleration due to gravity is 9.81 meters per second squared down. And on the surface of the Earth, that's a pretty good estimate of our acceleration. So this means that if you take any two objects and you neglect air resistance and you drop them from the same height, they're going to hit the ground at exactly the same time. Now, in real life scenarios, let's say if we were to drop a hammer and a feather on Earth in the classroom, obviously the hammer is going to fall to the ground before the feather does, but that's due to air resistance. This video, which I want you to watch right now, is a neat experiment that one of the Apollo astronauts did on the moon. On the moon, there's no air resistance because there's no atmosphere. So he actually took a little hammer and a feather up to the moon, and he dropped them both at the same height to see if they hit the ground at the same time. And actually, they did. And that's because the only force exerted on both of those objects was gravity. So they experienced exactly the same acceleration. Now this is a second video, which I want you to go watch now. And in this video, this guy makes this cool little machine that drops two pool balls, one with an initial velocity of 0 and another with some initial horizontal velocity. He records it with a high-speed camera to see if they will actually hit the ground at the same time. Now in this video, you can see that they do. This is a nice video because the air resistance experienced by both pool balls is really quite small, so it doesn't affect his results. So they do actually hit the ground at the same time. So obviously, if we give an object an initial horizontal velocity, it's not going to be influenced by the vertical acceleration due to gravity. So here's a nice little analysis of what's happening to that pool ball, just like in the video, when he launches it with some horizontal velocity. So let's just pretend that as he was launching it with the horizontal velocity, just like in this diagram, we take a whole bunch of snapshots as the ball is falling towards the ground. Now, if we were to draw some velocity vectors, and each vector represents the velocity of the ball in the x direction separately from the y direction, this is what it would look like. So first of all, in the horizontal, or x direction in our case, we'll call this y and we'll call this x. So in the x direction, it's initially only given an initial velocity in the x direction. Because there's no acceleration in the x direction, so we're neglecting air resistance, so there's no acceleration in the x direction, the x component of velocity will be exactly the same for every single snapshot. So for every single snapshot, you can just draw on a vector that is identical to every single other vector, and the magnitude is v1x, what it started with. Right before the pool ball hits the ground, we can assume it's still accelerating at that point, so it hasn't quite hit the ground yet. It hasn't touched the ground yet. Okay, so that's just the x direction. Constant velocity going on in the x direction. Now for the vertical direction. Initially, there's no initial vertical velocity, but after the first instant, it will start accelerating downward. So at that very first snapshot, it's going to have some very small vertical velocity. At the second snapshot, the vertical velocity will increase because it's accelerating downwards. At the third snapshot, the vertical velocity will increase even more. And finally, here we'll have the largest magnitude of vertical velocity because it will be accelerating for the longest amount of time. So obviously, in the x direction, this is a constant velocity scenario, but in the y direction, this is a constant acceleration scenario. Our y acceleration, or our vertical acceleration, is only influencing the velocity in the vertical direction. It doesn't impact the velocity in the x direction. And so that's exactly how we're going to approach all of these projectile motion problems. In order to analyze them, we're going to break the horizontal and vertical components into x and y coordinates. Y is going to represent our vertical direction, and x is going to represent our horizontal direction. This is useful because in the horizontal x direction, the ball or the object is traveling at a constant velocity, whereas in the y direction, the vertical direction, the object is always going to be accelerating downwards due to gravity. So what we can do is we can use our usual kinematics equations, those nice kinematics equations that describe constant acceleration problems, to analyze this motion. Although we have to treat both directions separately because one direction has constant velocity motion while the other direction has constant acceleration motion. So let's just summarize all of the equations we know so far. The easiest direction to analyze is your x direction because it's just constant velocity. So if we want to analyze, let's say, the displacement in the x direction, this is actually just our x velocity times time. Now notice I'm not going to write any vectors anymore in these equations. Instead, I'm substituting subscripts because this time I'm just breaking them down into each coordinate direction. So displacement, velocity, and acceleration, I'm going to include subscripts of x and y instead of using vector signs. Now, in the y direction, now x direction, that's it. There's just that one equation that relates the displacement in the x direction to the x velocities. Now, in the y direction, I'm going to write down those 5 kinematics equations for constant acceleration motion, except this time I'm going to use a lot of y subscripts because this motion is only for the vertical y direction. So let's go ahead and write them all down. We've got our first one, v2y equals v1y plus acceleration times time. That's our first kinematics equation for constant acceleration motion. Next, we've got displacement in the y direction is the time divided by 2 times the sum of the velocities. v1y plus v2y. Our third kinematics equation relates the initial velocity in the y direction. Oh dear. Okay, keep writing. Not sure why this is writing with me. Let's try that again. There we go. Delta t plus 1/2 acceleration delta t squared. Next step, we're still talking about displacement in the y direction, but this time we've got v2y, subtract 1/2 acceleration in y delta t squared. And finally, our fifth equation is v2 squared equals v1 squared plus 2 acceleration delta dy. So that's it. Those are our 5 possible equations. Again, whenever we're given a certain projectile motion problem, we're probably just going to need to choose one based on the information that we're given. We don't ever use all 5 at once. So that's it. These are the equations we're going to be using to analyze the motion. So now here's our first example. We've got a skateboarder rolling straight off a small hill with an initial velocity of 15 meters per second horizontally. So here's our small hill, really steep one. We've got a skateboarder at the top, there's his little skateboard, and he's going off the hill with some initial velocity, which is purely horizontal, so there's no y component to this velocity. We also know that the skateboarder's trajectory will be down like a little parabola. And we're also told that his whole fall will take 4 seconds. So here are the things that we know. First of all, I want to define coordinates. These are the easiest ones to define. So my y direction I'm going to call down positive, and in my x direction I'll call right positive. Now here's the things I'm given. The initial velocity is 15 meters per second in my positive direction, but this is really just my initial velocity in x. And it's purely in the x direction because it's purely horizontal. My initial velocity in the y direction is just 0 because there's no component of this initial velocity that is vertical. My acceleration is going to be 9.81 meters per second squared down, which based on my coordinate system, I'll just call the positive direction. That makes things a little easier. And now finally, I know that delta t is 4 seconds. And that's it. So now whenever I go ahead and solve one of these problems, here's how I like to lay it out, and I suggest you also lay out your solution this way. I have 2 columns to my solution. One represents the x direction and one represents the y direction. Now, in the x direction, I want to know where the skateboarder will be after 4 seconds. So where means what is his displacement in x and what is his displacement in y. So if I'm interested in displacement, here's the only equation for constant velocity. Displacement is velocity times time. I know that the velocity in the x direction is 15 meters per second. I know that he's airborne for 4 seconds, so therefore, I know that his range in the x direction, horizontally, is 60 meters. And I'm going to draw a little arrow just so I remember that that's 2 significant figures for later. Okay, now the y direction. So I already know that this, delta dx, is 60 meters. But now I want to know, what is this, delta dy? Since I'm given initial velocity in the y direction, acceleration in the y direction, and time, the equation that I want to use, so I can do this in one nice step, is this. So if you look at that equation, the only thing I don't know is displacement in the y direction, which is exactly what I want to find. So now I'll just substitute in some values. My initial velocity is 0, and my acceleration is 9.81 times 4 squared. So that gives me, when I substitute it or plug it in on my calculator, 0.5 times 9.81 times 4 squared is 78.48 meters. And this is where I want to round to eventually. Okay, now so far so good. I've got displacement in x and displacement in y. So if I really wanted to, I could say therefore, where is the skateboarder after 4 seconds? The skateboarder is 60 meters past, oh dear, the edge of the hill and 78 meters below. That technically describes his position after 4 seconds. But there's one other way that I can describe his position, and that's using displacement and taking it as a vector. So let's just zoom in a little bit. Nope, no good. Let's zoom in. So maybe it's like this. Okay, that's a little better. So now let's draw his displacement. We know that he's gone 78 meters, so 78.48, oh, 48 meters down and 60 meters past horizontally. So that means his overall displacement will be this vector right here. And of course, if it's a vector, we need to describe its orientation as well, so that's theta. So now, just like any other displacement problem, I want to figure out what is the magnitude of the displacement. I don't want that box. Go away, box. Okay, so I'm going to have to take the square root of everything. 78.48 squared plus 60 squared. So when I plug that into my calculator, here's what I get. 78.48 squared plus 60 squared, take the square root of the whole thing. I get 98.8 meters. But since I'm only interested, because remember, this one I was only interested to, not that one, the ones place. I've only got 2 significant figures. That's actually 99 meters. That's the magnitude of the displacement. However, I also want theta. Tan theta is O over A, opposite over adjacent. So that means when I calculate theta, I'm interested in 60 divided by 78.48. Notice how I'm not rounding 78.48. So tan inverse of 60 divided by 78.48 gives me, to 2 decimal places, 37 degrees. So now I just have to describe the displacement and the orientation. So therefore, the displacement is 99 meters. Oh, stay put. 99 meters. And here's how I'm going to describe, just move this to where I started with. Okay, 99 meters. And now I got to describe the orientation. So here's what I'm going to do. 37 degrees above vertical. Here's why I'm describing it that way. Here's vertical. Here's above vertical. So if something is above a vertical pointing down, I can say above vertical. That pretty completely describes its position in a horizontal vertical plane. That's it. That's the question. Next one. Here we've got an airplane that's dropping something while it's flying. This is a nice problem that comes up quite a lot in projectile motion. So we've got Charles Lindbergh. He's flying his plane at an altitude of 335 meters. His ground speed is 124 kilometers per hour. When is he directly over a pool? Oh, he is directly over a pool when he drops a penny. So here's, oh dear, here's the airplane. There's his airplane. It's going with this initial velocity, 124 kilometers per hour, when it drops a penny. When it drops the penny is initially traveling at the exact same speed as the airplane. So as it falls, it's going to have a parabolic trajectory because it's got some initial horizontal velocity, and it's going to be accelerating due to gravity. So in this case, is initial distance above the ground is 335 meters. We need to figure out what this displacement in the x direction is. We don't know yet. Here's what we do know. V1 is 124 kilometers per hour, which is our initial x velocity. Here's a red flag though. Kilometers per hour doesn't match this other unit we're given. So why don't we convert kilometers per hour to meters per second? So this is actually going to be 124, oh dear, kilometers per hour times 1,000 meters in a kilometer times 1 hour in 3,600 seconds. So we'll get V1x is 124 times 1,000 divided by 3,600. That's 34.444 repeating meters per second. I'm just going to draw a little arrow. So I'll use a lot of decimal places in my calculation, but I'll keep in mind it's only 3 significant figures. The other piece of information that I'm given is delta dy. I should also sketch my directions. Here's down, here's forward. I'll call those positive, since that's exclusively the motion I'm dealing with. Now delta dy was 335 meters down, but since down is positive, that number is going to be positive. And finally, the acceleration in the y direction is 9.81 meters per second squared down, also in the positive direction, so that's a positive number. Oh, and one more piece of information. Since its initial velocity was purely horizontal, it has no initial vertical velocity. So that's it. Those are my givens. I'm going to organize my answer by separating the x and the y direction. And then I'm going to start by writing down the equations that I need to use. In the x direction, this is my equation of motion for constant velocity motion. In this case, I know Vx. I want to find the displacement in x, but I don't know time. So I'm probably going to need to solve for time before I can solve this very easy equation. Now in the y direction, I know delta dy, I know the acceleration in y, I know the initial velocity in y. The only thing or one of the things I don't know is time. That's what I actually want to find. Now here is the equation I want to use. Okay, let's write it. No. Okay, delta t plus 1/2 acceleration delta t squared. I'm going to substitute in some numbers. This is 335 meters. This is 0 times delta t plus 1/2 times 9.81 times delta t squared. This term is 0, so that makes things kind of nice for me. I'll multiply both sides by 2. I'll divide both sides by 9.81. That's delta t squared. So that means delta t is 335 times 2 divided by 9.81, and I do want the square root of that, which gives me 8.2642 seconds, and I want to remember this is only 3 significant figures, but for the remainder of the calculation, I'm going to use all those decimal places, so I don't have any rounding errors. Okay, so now I know delta t for the whole trajectory until it hits the ground. That is what I want to use in this equation to solve for my range horizontally. So now all I need to do to find the horizontal range is substitute in my x velocity and the overall time, 8.2642. And I'm using lots of decimal places so I don't introduce any rounding error. So this comes out to be 284.657 meters. But since I'm only interested in this to 3 decimal places, that is 285 meters. So therefore, now was I asked for range explicitly? How far from the pool, which is like the horizontal range. So the penny will land 285 meters horizontally from the pool. So that's part A. That's not so bad. This one was a little bit tricky because we had to use information from both the x and y direction to totally solve the problem. But luckily our x direction equation is super straightforward. Okay, now B. What is the impact velocity for the penny? I'm going to redraw, for part B, I'm going to redraw the trajectory. Here's where it's released. Here's where it hits the ground. Initially, here's its initial velocity, totally. Finally, let's say this is its final overall velocity. Let's zoom in to this vector, v2. v2 is a combination of velocities in each coordinate direction, velocities that we can solve for using our kinematics equations. So there's some x component, which is actually exactly the same as our original velocity, and there's some y component, which we can solve for using our kinematics equations. So if we're given an acceleration of 9.81 meters per second squared, we're given an initial velocity of 0 meters per second, and we also know that the total thing is in the air, the total time it's in the air, we're talking about a penny still, is 8.2642 seconds. We have enough information to solve for v2 in the y direction. v2y is equal to v1y plus acceleration times time. So v2y is 0 plus 9.81 times 8.2642. In our calculator, this is just 9.81 times 8.2642, 81.072 meters per second. So now we know v2, and we know v1. It's the same as our original x velocity. We have enough information to solve for v2. So we can use this triangle here to say, okay, the magnitude of our velocity is just v2y squared plus v2x squared. And that's just 81.072 squared plus our initial x velocity from way up here, which is 34.44444 squared. Remember, this is good for three significant figures. So our magnitude is 81.072 squared plus 34.44444 squared. We want the square root of that whole thing. And we get to three significant figures, 88.1 meters per second. That's the magnitude. That's not enough, of course, because the velocity is also a vector. So we also want this direction, this angle here. Just like before, tan theta is opposite over adjacent. So theta is tan inverse of 34.4, oh dear, 4. Let's just turn these into, okay. 4, we'll call that a 4 over 81.072. Notice I'm not rounding at all, I'll round at the end. So in our calculators, tan inverse is 34.4444 divided by 81.072, and that gives us an angle of 23.0 degrees. So our final answer is the final velocity of the penny is 88.1 meters per second. And in terms of our direction, this is 23 degrees above the vertical. So we'll say 23 degrees above the vertical. Now, one other way of describing this is you could also say, since this blue line represents the horizontal and the complement of 23 degrees is 67 degrees, you could also equivalently describe this as 88.1 meters per second, 67 degrees below the horizontal. So that's just another equivalent way of describing the direction of that vector. Okay, that's about it for today. So you've got some homework to try. Make sure you check the solutions, which will be posted. And next class we'll be covering this again, except next class we're going to talk about situations where the projectile is given some initial velocity that has an x component and a y component as well. So have a good weekend, everyone.